Hi, in this video I'm going to talk about question number 7 of homework 9, probability and a stochastic processes course. Let's dive into the question first. So, in question number 7, we want to show that the random telegraph signal is a strict sense stationary process. To solve this problem, you should first know the definition of a strict sense stationary process. A process is a strict sense stationary if the joint unconditional probability is equal to the case that we shift in time. So if we want to write this using mathematics, we can write it like the probability of y of tn equals to yn till the probability of y of t1 equals to y1, which is a joint distribution, is equal to the probability of ytn plus epsilon plus a shift in time, which is epsilon, equal to yn till the y of t1 plus epsilon equal to y1. So these two joint distributions, if these two joint distributions are equal to each other, then we can prove that our stochastic process is SSS. To solve this problem, we need to use some example. And let's first define our example. For defining our example, we can show this, that we had in the previous homework, that if we have a some process with lambda parameter, we can define some x of t which is equal to 1 if n is odd and equals to -1 if n is even. And as you can see, the figure of x of t is very close to the telegraph and sending a signal. And in this homework, we showed that we can write, let me bring my answer to this question. Yeah, we showed that the probability of k being equal to an even number, is equal to the e to the power of minus lambda t times cosine hyperbolic of lambda times t. So we can use exactly this into our problem. So let's dive into the answer. So we have this figure, and we write the probability of y of tn equals to 1 given y of tn minus 1 equals to 1 till y of t1 equals to 1. We can omit all of the previous states. Only the most current previous state is enough to calculate this. So it is equal to the probability of y of tn equals to 1 given y of tn minus 1 equal to 1. And from the example that I showed you, this is equal to the e to the power of minus lambda, and the time interval, which is between tn and tn minus 1, and the cosine hyperbolic of lambda, and again the delta time. Okay, so I have set up my example now, and I can go back to the joint distribution, which I had. And if I write the definition for the joint distribution using the total theorem, I can write as the probability of y of tn equals to 1 given all of tn minus 1 till t1. And again, for times the probability of joint distribution of tn minus 1 till t1. Again, I can write it like a conditional distribution till the end. And as I said earlier, we can omit the previous states to t1 and only keep the most recent previous state for each of these. So we will have the probability of y of tn given y of tn minus 1 times the probability of y of tn minus 1 equals to 1 given y of tn minus 2 equals to 1. And we can continue this till t2, y of t2 times y of t1 times the probability of y of t1 equals to 1. And as you can see, we can substitute all these conditional probabilities with the term which we had here. And you can see that in all of the terms, we have ti minus 1. So here we can see that each of the terms just depend on ti minus 1. And so the proof is completed. So the epsilon in any shift in time is going to be omitted because we have ti plus epsilon minus ti minus 1 plus epsilon. And those epsilons are going to be omitted, and our process is SSS, and the shift in time does not influence the joint probability. Thanks for listening to me.